Hello everyone, hope you're having a better day than me. As usual, we watched this before class. What's special today is we are starting the next topic, laminate macromechanics. It is chapter 4 in your textbook. Chapter 4 in textbook. Why? Because no one uses just a single lamina to make a structure. It's not enough. No one even makes a lamina all with the same orientation. For example, if you use all 0-degree plies, then it's not really useful in any other direction. If your major load is along the fiber direction, then yes, good. But otherwise, we don't really use just unidirectional fibers or unidirectional laminas. We use a combination of different plies or orientations. So this behavior, how does stacking up different plies together in a certain way behave? So that laminate behavior is influenced by all these bullet point properties. So one, of course, is the elastic moduli of the different fibers, different resins, and then the stacking position. Stacking position means what ply is on the top, what ply is on the bottom, what ply is in the middle, right? So if you have, let's say, a composite of 0 degrees, 35 degrees in the middle, and then 45 degrees at the bottom, it would behave in a different way than if, let's say, 35 degrees is at the top, 45 degrees is in the middle, and 0 degrees is at the bottom. So even if it is the same combination of plies, if you change the order, the laminate behavior changes. And of course, the thickness also matters of each layer, and then the angles of orientation, theta, what are the angled plies you're using, and coefficients of thermal expansion and moisture expansion. Thermal expansion, if you remember, alpha 1, alpha 2 for each ply, and moisture expansion, beta 1 and beta 2 for each ply. Usually each ply is said to be about 0.005 inches thick, which I believe is about 0.125 millimeters. So that's the usual thickness, and the orientation or the coordinate system that we use is the cross section is x is the normal, and z is the downward axis. So what is the major change is, instead of y, you're going to be using z for your vertical axis, and it's the positive is always down. So for the cross section, we'll see the cross section picture in a second. I'll show you. So then there is a particular way in which you write or you communicate a particular stacking sequence. So what are the rules to be followed? Let's say you have 0 at the top, and then minus 45, 90, 60, 30. So you start by putting these numbers inside square brackets and with slashes in between them. So the negative is missing here. So square brackets and then numbers and then slashes in between them. So this is how to write or represent a laminate stack. But there are, of course, different types of special cases. Let's see what are those. Writing this way is called laminate code. For example, if you have this particular type, 0, minus 45, 90, 90, 60, 0. So square bracket, 0. It was this way, correct? 0, minus 45, slash 90. But because you have two 90s continuously, you can write 2 in the subscript, slash 60, slash 0. Close the square bracket. This is how you write if you have repeated plies. If you have something that looks like this, 0, minus 45, 60, 60, minus 45, 0. So you can see about this plane, the stacking is symmetric. So in this case, you write it as 0 slash minus 45 slash 60, but then close the bracket and say yes as a subscript. So that tells you it's a symmetric laminate with 0, minus 45 and 60. So the other three plies are 60, minus 45, 0 backwards. But but this is even, so this is easier. What happens if you have the odd number of plies, where you have 0, minus 45, 60, the 60 does not repeat, minus 45 and 0. It is still symmetric about this plane, correct? So then what do? Same technique, 0, minus 45, slash 60, but over the 60 add a bar and then close and then say S. So it means in this symmetric laminate 60 is not repeated. And then you have possibilities of laminates where you have different materials even. So in that case, what do? You say, for example, here it's 0, 45, minus 45, minus 45, 45, 0. So it is symmetric about this plane. So then you say 0 slash plus minus 45. Close, write S for symmetric. So it's 0 plus 45 minus 45, minus 45 plus 45, and then 0 again. So if you write minus and plus 45, then the minus layer goes first. That's the meaning. So here, because they are also made of different materials, you have to mention that graphite, Gr, 0 are graphite, plus and minus 45 are boron. So this is how you write laminate codes or the stacking sequence. So there are special types of laminates. Symmetric we just saw. Balanced laminate. So if you have a plus theta ply, then there will definitely be a minus theta ply somewhere. It need not be symmetric. That's called a balanced laminate. And cross ply laminate is one that has only 0 degrees and 90 degrees. For example, this is your ply. This is your 0 degrees. So then the other layers would be composed of 0 and 90 degree plies. Only those in some combination, it's called a cross ply laminate. And then quasi isotropic. What does that mean? It exhibits isotropic properties in the extensional stiffness direction, right? That is in the E1 direction. So exhibits isotropic extensional stiffness properties. So when do you get this? This is a special case produced using at least 3 different ply orientations, all with equal angles between them. For example, if you use 0 degrees, 30 degrees, and then 60 degrees, right? So they all have a difference of 30 degrees, or you can be 30, 60, 90, right? So some kind of combination with 3 different orientations which have the same difference between them. That very weirdly or strangely exhibits isotropic properties in the extensional stiffness parameters. So then we come to, as always, how to calculate strains, how to calculate stresses. So let's say in your beam you have centric or axial loading. Axial load, you all know, it goes through the central axis of your structure. In that case, you know how to calculate stress. Stress equals, why is my colon very strange? It's fine. Stress equals, or sigma xx equals P over A, force over area, which means you can get strain. Strain equals stress by Young's modulus, right? Strain equals stress by Young's modulus, Hooke's law. So it's the same thing. So epsilon xx equals P over AE. This is due to the axial load. What happens if it is subject to rotation like a beam? If you remember from solid mechanics, we are actually doing the topic of bending in solid mechanics now. Normal stress equals, normal strain equals, you should remember that M causes, or bending moments cause normal stresses, right? Torsion causes shear stress. So here, because we're talking about bending moment, normal stress, normal strain is actually equal to minus y by rho. So here, because the vertical axis is z, right, your epsilon xx is actually z by rho due to bending, and the minus has gone away because your positive is z downward. And then if you forgot what rho was, I'll show you. We assume one of the major assumptions that we make in the bending calculation is that our beam, if it's subject to rotation, in this case, if it's subject to rotation, it will rotate, or let me draw it this way. So however it bends, this way or the opposite way, it always bends in the form of a smooth circular arc, which means it's part of a circle with the center somewhere at C, but the radius is called the radius of curvature. How much it curves is denoted by the symbol rho. So here you can see if it's axial load, it causes normal strains. If it's rotation or bending, it causes normal strains as well. So in real life, you always have a combination of these loads, which means your normal stress or normal strain, epsilon xx, is a combination of both P over AE plus Z over rho. So the P over AE is denoted as epsilon naught and Z into 1 by rho. So epsilon naught and 1 by rho is actually shown by another symbol here. Slightly weird looking lowercase k. So k is kappa. The symbol is called kappa. It denotes curvature. How much our beam is bending. This epsilon naught is the mid-plane strain. Why is it mid-plane strain? Because the axial load passes through the center, passes through the middle plane. So it's the mid-plane strain, and plus Z is the distance away from the mid-plane multiplied by the curvature. This is your total strain. So now we go to talk about how the stresses and strains are related. So the theory is called classical lamination theory, or CLT in composites. Of course, as always, we make quite a lot of simplification or assumptions. So the first two assumptions we make is that each lamina is orthotropic. We're not simplifying that, but we are saying each lamina is homogeneous, even though it consists of two different materials of fiber and resin. You're saying just look at it from the macro level. In a lamina, at any point, you have a particular property, which, if you remember, was E1, E2, major Poisson's ratio, right? Things like that. And then, is it done? Moving. A line straight and perpendicular to the middle surface remains straight and perpendicular to the middle surface during deformation. This, I don't know if you remember, in SolidWorks, when we talk about, solid mechanics, when we talk about bending, you have this beam, and then it is separated into these grids, and it's shown, the assumption says that even after it bends, the 90 degrees remain 90 degrees. They do not change into rhombuses, like when you shear them. So that is one of the assumptions we make. Why it's very helpful? Because then you can say your shear strains are 0, which in turn make your shear stresses tau xz and tau yz to be 0. The only non-zero strains and stresses are tau xy and gamma xy. Laminate is thin, loaded only in its plane stress, which means there's no normal stress in the z direction. There are no shear stresses in the xz and yz plane. So only tau xy and gamma xy are non-zero. And then we're saying all our displacements u, v, w in the x, y, z directions are continuous and small when compared to the laminate thickness h. It is the thickness in the z direction. Each lamina is elastic, and then it doesn't slip between the lamina interfaces. So these are the basic assumptions we make for this particular theory, classical lamination theory. So what are the types of load, or what are the types of loads that we analyze? It's normal forces and moments. Normal forces are always per unit length, because we don't really talk about the width or the length of the beam or the rod. It's always Newton per meter. Similarly, your bending moments, mx, my, and mxy, which is a twisting moment, which we usually denote by the symbol T, right? they are also per unit length. This is very, very important. So it's Newton meters per meter. The meter and meter do not get cancelled, do not become newtons. It's bending moment, rotation per unit length of your structure. So this is your cross section. It's the XZ plane. Y is the length of your structure. So here mid plane, so it's h over 2 and h over 2. Let's consider a point A at a distance z from the middle plane. So then once you have that, let's see how under a certain loading, let's say a combination of loads, it moves, right? It rotates a bit. So then what is the position? Let's call this A prime. What is the position of A prime now? So before that, because we always start talking about mid plane because that is easy. The mid plane, if you remember, for a rectangle is the neutral axis. It does not get tensed or compressed, right? So then it moves, it has translated across space. U naught distance from the starting point, and W naught distance in the z direction, and V naught you cannot see, but it is that V naught in y direction. This is the mid plane movement. But if you want a random point such as A, what has become of A prime? Then you have to think. This is Z alpha, the alpha is missing. This is also alpha, this is also alpha. We'll talk about alpha in a second. So if you remember from the first topic, we defined strains in terms of partial derivatives. Strain in the x direction was dou u by dou x. In the y direction was dou u by dou y. Here, because we want to keep it simple, we are only going to do 2D, not 3D. We are only talking about the cross section. So, and then gamma xy shear strain. So combination of dou u by dou y plus dou v by dou x. So these were the definitions of strains in our first topic. So now we are going to find these strains as well. For example, let's start talking about UA. How much has A moved in the x direction? So the mid plane has moved u naught, but A has not moved that much. It is actually u naught minus something. How much is it minus? It is minus this distance, right? So if you consider this right angle triangle, if you write tan alpha, let's call this unknown x, tan alpha equals x divided by the location of A, or the distance of A from the midplane was z, so x by z. So if alpha is a very small angle, because that was one of the assumptions, all deformations are small. So then we say x equals z times alpha. That is what is denoted here. So then UA equals u naught minus z alpha, right? And then what is alpha? Alpha, if you think about it, the mid plane has moved, right? Mid plane has moved or rotated, right? So then that this angle, right? It is the angle between the horizontal and the vertical. It's basically alpha is the slope of the moved midplane. So alpha equals, if you look at it as slope, it is actually dou w naught by, which is the vertical displacement, divided by the horizontal, which is x. Slope is rise over run, right? Dy by dx. But because it's a composite, everything is influenced by everything else. It's all dependent on each other. We cannot use total differential like we use for beams in solid mechanics, metallic beams. Here it's dou w naught by dou x. So if you substitute this value in this equation, then UA becomes u naught minus z into dou w naught by dou x. If you substitute this equation into your strain equation, into this epsilon x equal to dou u by dou x, then epsilon x equals dou of this whole thing, u naught minus z dou w naught by dou x divided by dou x. So if you simplify, you get dou u naught by dou x minus z is a constant value, it's a distance number, so z you're not going to differentiate, z into dou square w naught by dou x squared. So this is a double differential. So this is your strain in the x direction caused by translation and rotation. So similarly, if you simplify for other directions and shear strain, you have this equation epsilon x, epsilon y, gamma xy. So epsilon x is dou u naught by dou x minus, because we are writing it in matrix form, we do plus z, the minus is inside, minus dou square w naught by dou x squared. Similarly, strain in y direction epsilon y equals dou v naught by dou y minus z into dou square w naught by dou y squared. Gamma xy shear strain equals dou u naught by dou y plus dou v naught by dou x minus z, or because here it's shear strain, minus 2z into dou square w naught by dou x dou y. Here, so we write it in short form, the u naught, v naught and the shear strain is all for the mid plane. These are called mid plane strains. And these square terms, if you remember from solid mechanics, your beam deformation was d square y by dx square. I think so. So this is what you have for a metallic beam in solid mechanics. So similarly here you have dou square w naught by dou x square, dou y square and dou x dou y for the shear strain. So these in short are written as plus z into the minus dou square w naught by the dou x dou y and dou x square, all of them are called or denoted by the kappas, kappa x, kappa y, kappa xy. These are curvatures. So basically you're saying strain, total strain is a combination of your mid-plane strains epsilon naughts plus z into your curvatures kappas. So from that, how do you get stresses? You know this, we already know this. Sigma equals q bar, which is your reduced transformed stiffness matrix, 2D matrix. It accounts for the angles also, angle applies using the transformation. Q bar into epsilon or strains. So stress equals stiffness into strain. So this you already know. The only difference is that now the strain is split into mid-plane and curvatures. And of course, don't forget the Z here. The K stands for kth ply. You have to go ply by ply. Simplest way to visualize is, let's say you have a laminate made of 3 different plies, thicknesses, etc. From our basic strain equation, if you remember, epsilon was, in terms of bending, it was minus y by rho or z by rho, correct? So which means your epsilon is, in this case, proportional to y, which is the vertical. So that's why you have this linear variation of strain. But of course, each layer has its own modulus. Modulus is different. That difference in properties is reflected as a non-linear stress variation. The stress, as you can see, jumps when the layer changes. And as you add more plies, it gets more complicated, or the jumps vary. So when you have more plies, this is how you start counting it from the mid plane. So Z downward is positive, XZ. So this is your cross section. So you go H naught is the first layer, and then you have H1, H2, H3, and so on. As you go downward, it's if you have HK, this is HK minus 1, this is HK plus 1, and the last one is HN, HN. Right, so for example, this is H1, this is H1 minus 1. And we usually assume the thicknesses to be equal. T1 equals T2 equals so on to Tn. So this is one of our major assumptions as well. And then the last slide for today is just reiterating what we've learned till now. Total strain equals a combination of mid-plane strains and the curvatures multiplied by the distance z wherever you're calculating strains. And of course, using the Q-bar matrix, you can find stresses. So strain variation is linear, and you can see as the number of plies goes up, as they differ in thickness and properties, the stress jumps. Non-linear jumps. So before you come to class, I hope you go through what Q-bar is or how to find the Q-bar matrix. That will be helpful when we talk about how if N and M are applied, then using those values, how do you get stresses, strains, or if the stress and strain are known, how do you calculate what loads are applied, right? So this relationship, of course, is going to be other matrices. For that, the Q-bar matrix is important. So we will learn all of these relationships and we will do an example problem in class. If we have additional time, we'll do answers. That's it for today. Have a good weekend, everyone. Bye-bye.